Here we are going to learn about the directive influence of the substituents on benzene. Before understanding what is a directive influence of the substituents on benzene, let us understand why we are learning this. Okay, why? That is what is very important. Whenever we learn something, why we are learning that. That is what is to be focused. If you want to prepare this compound, there is a benzene, there is a bromine, and there is a nitro group over here. Now it's very simple. Someone will say that we need to do the nitration of the benzene and then do the bromination. Some may answer that okay, we can do bromination first and then nitration. Now we have to focus that whether doing both the processes, like doing first bromination and then nitration, or doing nitration first and doing bromination, is one and same. Okay, what is the thing? Like if we are preparing this, doing bromination is okay and then doing nitration, or we have to do nitration first and then bromination. Like these two questions will arise, and doing both way is one and same. So this type of answer, this type of questions will be answered by understanding the directive influence of the substituents on the benzene. So let's start with it. There is a benzene. Let's say there is a monosubstituted benzene. Let's say this is a compound. There is a benzene and there is one molecule A. It could be a nitro group, it could be a OH group, it could be a halide, it could be anything, right? But there is already one group present on a benzene, and if you want to substitute something B, okay, B, let's say this is the electrophile. If you want to do the substitution of this electrophile B on this benzene, then where it will go, right? The possibility is that it can go over here. The possibility is that A can go, B can get substituted over here, or B can get substitute over here, okay, or there is this possibility, B can get substitute over here, okay. These are the possibility. So this type of answers, this type of questions where the incoming electrophile will get substitute on a mono-substituted benzene. Like if it is a benzene, that won't be a problem. Like if it is a pure benzene, just benzene is there are no any substituent. If you want to add this electrophile anywhere, then it is one and same wherever it go. Any position is equivalent, but already there is one substituent on the benzene, and where the incoming electrophile will be going, whether it is ortho position, whether it is meta or the para, that is what we are going to learn. So first thing is that I will categorize. There are ortho, para, directing, activating groups. Okay, this is one category, ortho, para, directing, activating groups of the benzene. Means benzene will get activate, means benzene will become more electron rich, and the incoming electrophile will get at the ortho and at the para position. There is another category, that is meta, directing, deactivating groups. Deactivating groups means these are the groups which will reduce the electron density from the benzene. It will pull out the electron density from the benzene, and incoming electrophile will go at a meta position to the substituents which is already present. And there is a third category I will mention about it, that is ortho-para directing, deactivating. Incoming electrophile will go at ortho and para, but it is deactivating. Okay, it is going to pull the electrons outside from the ring. It is going to make the electron, it is going to make the rich electron deficient. So let's go ahead with this. Let us understand, okay, let us understand a first thing, that is orthopara directing deactivating group. Sorry, activating groups. Let's take this. The groups which are like this NH2 means, I will summarize the groups which will be activating groups, and incoming electrophile will be going to the ortho and the para position to this. That is first is NH2 group. Okay, there is lone pair of electron. I can further still generalize NHR. One of the hydrogen is replaced with R, that is, it could be a methyl or ethyl, any type of group further. Then this is NR2. Both will be alkyl group present on the nitrogen. It could be this OH group, or it could be COOR group, or it could be just R group, which shows the inductive effect plus I effect. Now over here, let's take one example, NH2. Why, if this NH2 is there, what is the meaning of this? Ortho-para directing group. If this group is there, and let's say if I want to do the nitration, over here, let's replace this with the OH. OH will be much simpler because there are lone pair of electron in this, right? And let's say if we want to substitute the electrophile E, let's say I want to substitute the electrophile E, where this electrophile will go, I will get the two products. Generally I will get two products. One is OH, and here will be the E because it is a electrophile E, and this may be a minor product, like lot of repulsion, less stable, and other will be a here will be a E. This is major product. This is ortho position, and this is para. Now why this is so? Why incoming electrophile either gets substituted at ortho positions or at the para? If we see the resonance structure, whenever such type of groups are there, let us understand this by a resonance structure. It's very simple. Let's take a resonance structure of this. This is OH. Okay. So where this is going to move? Here there will be a resonance. It will be donating its electron to this conjugation, right? I will mark it in this form. This is electron reach. So obviously this is going to shift over here because this is the oxygen which is connected to this carbon, and this carbon is a partially positive. Oxygen is electronegative. This is partially positive. That's why this electron is going to move over here. If it is moving, that carbon cannot withstand more than 5 bond. One of the pi electron will shift on this carbon. Means next resonating structure what you get over here is this. Right, and here there will be a double bond and the positive charge, and what you can see is that a negative charge will be formed over here. Further, this is the thing, this is how the resonance is going to take place of the band. Further, just draw all the resonating structure. Yes, this will be the resonating structure of the benzene. Means here electrons are donated to the benzene. See, benzene is electron rich. There are pi electrons into the benzene, and also this oxygen is donating its electrons. So there is more electron density in the benzene. Since there is more electron density in the benzene, what I can say in the other word is that the electron density of the benzene will be increased. If that electron density is increased in the benzene, what will happen? The electrophile substitution will be much better. Like normal benzene you take and you compare that with a benzene when there is a electron donating group like OH or NH2. That time the reactivity of the benzene will be much more than that of the normal benzene, right? So here, why? Because electrons are donated. That's why this is called as activating group. These are the activating group. And why? You can see that the negative charge, if the negative charge on the benzene structure in the resonance structure is either at ortho position, this is a ortho position, or this is para position, or it is at another ortho position, right? So negative charge is there is more electron density at a ortho or para, never at meta. So incoming electrophile will get substituted either at ortho or at para. So this is the concept of the um, directive influence of the ortho-para directing activating groups. So this is the thing. Next, let us understand what is meta directing deactivating groups. So next is meta directing deactivating groups. Examples are, right, which are the groups which will deactivate and the incoming electrophile will be directed towards meta position to this group with respect to this group. NO2, then there is cyanide, then you can also consider CHO, that is aldehydic group, or carboxylic group, or this group. There are many more. These are the groups which will show a meta directing. And why it is called deactivating? Let us have a look. Like if these groups are there, okay, let's consider these groups are there. NO2 group is there, and let's say there is some electrophile E. There is some electrophile E. Now where it will get substitute? Where it will get substitute? You will get only one product. You are going to get just one product. That is NO2, and E will be getting substituted to the meta position. Let us understand this by the resonance structure of the nitrobenzene. So I'll just draw. Just pay attention while I draw how I am doing this. NO2. If it is NO2, then it is this way. And there is a positive charge. See, electrons are there in the pi. Here there is a pi electrons which are comparatively more free to move than a sigma electron. When sigma is there, then it will break, but pi electrons are more easy to move. So where it will get attracted? It will get attracted to this positive charge right here. So in the resonance structure, this carbon is going to lose its electron. So that carbon will have a positive charge. Then further these pi electrons will be shifted because there is a positive charge here. In this whole process, what you can see is that it is a positive charge density, it is at ortho and the para. But if you compare, like if this is positive, these positions are positive, these positions are positive at these three things, means if this is the benzene, if this is the ring, then here and the here are the positive, means there is less electron charge density. And which are the position left? Let's see, this is a group where A is there, that is a electron withdrawing group, meta directing. So if that is there, then here if you compare among these sides will be more electron rich, because since these are positive, these will be, there is no positive, there is no negative on this, but still if you compare among this, then these two sides, meta sides, will be electron rich. So there is no option for the electrophile will be getting at a substituted at a meta position at this and this, it is one and same, right? So why it is called deactivating? What happens? These are the groups which withdraws the electron density from the ring. These are the groups which withdraws the electron density from the ring. So the benzene ring is negative, and because of the presence of this group, like there is a withdrawal of the electron from the benzene. So what will happen? The electrophilic attack will be less violent. What we can say, the reaction will be little slower compared to that of the benzene. So that's why these groups are called as a meta directing deactivating groups. The incoming electrophile will be getting directed to the meta position and it is deactivating the ring. Third category is I will write orthopara directing deactivating groups. Waiting groups. Okay, which are those groups? These are the halides like chlorine, bromine, and iodine. These are the groups which are, it will direct the incoming electrophile to the ortho and para position, but it in fact going to deactivate the ring. Deactivate means what? The reactivity between the benzene ring and the electrophile is going to decrease, because it is going to pull the electron to the inductive effect. See, halides, if I am considering the halide, then it is this. I will just write some example. Let's take a bromine. How many lone pairs are there? There are 3 lone pairs of electron on the benzene, and this is also going to show the resonance structure this way. I'll do this quickly. How the structure is going to be. It is donating an electron through a resonance effect. It is donating an electron to the benzene through resonance effect, right? Right. So this is the structure which you are going to get, and if you observe, the negative electron density is at a ortho and para position. Then why this is called as a deactivating group? Why this is called as a deactivating group? See, it is donating an electron through the plus R group, like plus resonance. It is donating an electron, but when it comes to the halides, there is a minus I effect, and here minus I effect, inductive effect, and is more dominant. It is withdrawing the electron, and it is withdrawing the electron because of the high electronegativity of the halides. So that's why no doubt the incoming electrophile will get substituted at a ortho and para position, but it is going to decrease the reactivity of the benzene because of the inductive effect. That is the only reason. Let's come to our question. Like first question, which was, I said that a nitro and the bromobenzene, nitro-bromobenzene, I showed one structure. If we want to prepare this, from benzene, let's say this is nitro and this is Br. If you want to prepare this, some will say that it is nitration. Like we will take a benzene. If we take a benzene, we'll do the nitration of benzene first. Okay, we'll take a benzene and NO2 is the electrophile which will be there and it will get substitute over here. It will get substituted over here. Then do the bromination. Let's see, are we getting this product? Okay, now I am doing NO2, right? NO2 is a meta-directing group. NO2 is a meta-directing group, and what we can get is, yes, we can get this product. We will get this product, that is NO2 Br. Now just think of this reaction opposite. You are doing bromination first and then doing a nitration. Let's do it that way. Let's do the bromination first. And then nitration. And let us see what we are going to get. So I am doing bromination and this is benzene, and here bromine as a electrophile by some means it is getting substituted on the benzene, and this is your bromobenzene, and now you do the nitration on the bromobenzene. The what product you are going to get? The incoming electrophile, that is this is what type of group? It is a ortho-para directing group. It is deactivating, but it is going to direct the incoming electrophile to the ortho and para. So my product will be this way. Br, one product will be NO2 and other product will be Br and NO2 over here, and never add this. So you are not going to get this product. So for such type of reactions, understanding the directive influence of the monosubstituted benzene. Okay, if we are doing the second time substitution of benzene, that time we should know the what is the directive influence of the group already present on the benzene. So I'll end this class over here. Thank you so much. See you in the next lecture.